All righty, ladies and gentlemen, boys and girls, welcome to another exciting episode of Mr. Smith Talks About Calculus. Today featuring my lucky Ren Spooner Dodger shirt, because this morning is October 20th, year of our Lord 2020, game one of the 2020 World Series, in which Clayton Kershaw will take the mound against the highly touted Tampa Bay Devil Rays. Actually, I think they're just the Rays. They dropped the Devil. And so I'm stoked on that. And I'm also stoked to bring you the first installment of Chapter 3. It's going to be good. So let's get to it. As always, I recommend cranking her up to 1. Oh, did it just start recording? I never know exactly when it starts recording on Zoom. And being honest, it just says recording. I think it just started blinking. So you might have missed the part about me bloviating about Clayton Kershaw and the Dodgers, but we're going to win tonight. Anyway, Chapter 3 leads off with, that's not where I was going with that. I was saying something, whatever. Anyway, we're going to jump into Chapter 3 since we all rocked Chapter 2, hopefully. And the first thing we're going to do in Chapter 3 is look at one of the main applications of the derivatives as it relates to the graphs of functions. And one of the primary uses of the derivative, which again gives us the slope of our tangent line to a curve at a given point. So think about that visually, that tangent to a point, it's going to let us zero in on when a function has a maximum or a minimum value on a given interval. Okay, if you can remember like Algebra 2 pre-calc, when we did our polynomial graphing, we were kind of just guessing the turning points. We're like, yeah, sure, whatever. Like we knew the x-intercepts, we knew the y-intercepts, but in terms of like where the bumps were, we were kind of guessing. Well, calculus is going to give us the tool starting today to stop guessing and to know, oh, well, if you got a flat derivative there, zero derivative, horizontal tangent line, there's a good chance, not a perfect chance, which we'll see, but a good chance that you've got a maximum or a minimum and a turning point on your curve. And so we're going to look at that today and see how to identify those potential max and min spots and use the derivative to do so. So it's going to be a real doozy. I think you'll enjoy it. It's going to be good. Oh, that's what I was going to say. Turn warp speed up to 1.25, or if you're really crazy, I think Edgar said he does this, 1.5 speed. That might be a little much, but you do you. Make sure you're taking these notes. And let's do this. All right, share screen. Content from second camera. Please work. Oh, there we go. Love it when it works. And I'm already ready to go with the title, just so prepped today. 3.1 maximum and minimum function values. Cool. And I think, and maybe this won't work very well, but sort of just sifting through my notes from last year and the book pages, I think I'm going to change things up a little bit in the presentation here. Don't get me wrong, I love Louis Lighthold, good dude, wrote a great textbook, but sometimes the presentation of topics is a little bit definition heavy at the beginning, which we'll get to those definitions, but I want to just kind of throw the big idea at you that's coming out of this section that I kind of just hinted at when thinking about curves and stuff. But the big idea is this idea of critical numbers where we might have a maximum or minimum value. And the idea of a maximum or min, I'll give you those definitions, but I think intuitively you understand what I mean. Like you look at a part of a function and there's like a maximum function there, might not, or a maximum value, might not be the max value for the entire function, but within a certain range, that's the biggest value or the smallest value. And where those happen can be hinted at by specific outcomes of our derivative, okay? And so those specific outcomes and the places they happen are called critical numbers. And so the starting point on all the problems we're going to do with max and min starts with critical numbers. And so I think starting there with our exploration today might be a good place. You know, lead with what's important. And so what's important today is establishing what a critical number is and how to find them, and then how to verify whether that critical number in fact is a maximum or minimum on your function, because it's not always the case. They're kind of just like potentials, kind of like, if you remember the rational root theorem, just gave you the potential rational roots for a polynomial function. Didn't guarantee that any of those things were roots, just that they could be. So too with our critical numbers. Now I've said critical like 17 times. Let's just tell you what a critical number is. So you're gonna freak out, but we're skipping way ahead to 3.1.4 definition. What happened to 3.1.2 and 3.1? Don't worry about it. We'll come back. We'll be okay. Okay. So 3.1.4 definition of a critical number. I mean, just the name, you know, makes it sound important. Critical, you know. We've reached critical mass, you know, critical. Kind of get your back of your neck hairs up a little bit, like, oh, what's going on here? I don't know what it is, but it's critical. Critical condition, critical number. All right. And again, I'm probably going to bore you with this definition because sometimes that's how definitions are. Then we'll see how it works. So if C is a number in the domain of the function f, do we want a light here? Does that help? Yeah, sure, why not? Turn this over to what's going on? What's going on? I don't know. It's Tuesday. In the domain of the function f, and if the derivative of f at c, so c is some number in the domain, and if the derivative of our function at that number c is 0, should indicate a horizontal tangent, or the second possibility, if the derivative of f at c don't exist, dne does not exist, then c is a critical number of f. Okay, so those are our two things we're hunting down with our derivatives. In order to help inform our picture of what our function is doing, if we can find the places where our derivative is 0, and thus horizontal tangent, or if it doesn't exist, which that's a little bit of a trickier case, but we'll do some visual examples to kind of get a sense of why that might point to a max or a min. But if one of those two things is true, then we have a critical number, and then we have a potential maximum or minimum, okay? These two conditions are not sufficient to tell you that they are locations of a maximum or a minimum, but they are necessary, okay? Without one of these two, you do not have a max or min, okay? So, and now we keep saying max and min. Well, no, let's write that down because this is important. Who cares about critical numbers? We care because they're critical. Duh, run over that. Pay attention. Critical numbers. Let me just make sure I'm not botching this too bad. Probably already have, but it's okay. Nobody's here to tell me I'm doing it wrong. I'm in an empty room, so. Critical numbers. This is kind of like the Y. Let me put a star here. Critical numbers point to locations of potential being a big word here, potential maximum or minimum values. Cool. Do we need to spend time defining maximum and minimum? No, I think we'll survive if we don't formally define relative max and min. Okay. Maybe we should. Maybe we should. Now I'm second guessing. Now I'm doubting. But I think relative mins are important. Relative max and mins are important to define, if for no other reason than to when we get to the absolute maximum or minimum value at the end of this section. The discrepancy between the relative min being on an open interval and the absolute min being on a closed interval, that will come up time and time again on your AP test. So I think maybe with that view of things, we will return to the beginning. So we start in the middle, we're going back to the beginning, and then we're going to tie stuff together. Okay. But I think I'm going to just do this as one definition because we don't need to. So we're going to do this all in one fell swoop, 3.1.2 and 3.1.1. I don't know why I just wrote in that order. Definitions of relative maximum and minimum values. Okay, so the function f has a relative max or min. We're going to define these both at once because they're literally identical except for the last line. At the number c, if there exists an open interval containing C, on which C is defined. That's important. In order to be a max or a min, you have to actually have a function value there. Containing C on which C is defined such that, and this is where the definitions divert. If it's a max, the such that we need is that f of C is greater than or equal to, that'll work, greater than or equal to f of x for all values x in that interval. And that, of course, would be for the max, or the opposite, if f of C is less than or equal to f of x, that would be for the min. Okay. I think the thing that I'm just going to highlight here, and maybe the reason we did this, is that this is on an open interval. This is on an open interval. Okay. At the end of this section, we will talk about absolute maxes or mins, these being relative. At the end, we will have absolute, and those require a closed interval. And that is kind of like a AP, like, who's the dog? Who's the dog that got trained with the bell? I want to say Maslow, but I know that's not right. You know what I'm talking about. Like, that's like a reaction that needs to happen when you're taking the AP test. Like, oh, closed interval, critical numbers, they're asking about absolute extreme. Okay. Pavlov's dog. Okay. Pavlovian response. Yeah. Yeah, because that's what education is, just Pavlovian responses, no free thinking or critical thinking, just stimuli, response, stimuli, response, stimuli, response, okay? kind of tongue in cheek here, but also kind of true. So kind of towing that line. Anyway, Mr. Smith going off the rails. What else is new? It's Tuesday. And then these things we call collectively relative extrema. Okay, relative extrema. So if a function has a relative max or min at a given number, at C, then the function has a relative maximum. Sorry, no, not relative extremum. Pay attention. Extremum. Also kind of a scary sounding word. Oh yeah. So now we've got kind of the key players defined. Like we now have the language to talk about what we need to talk about. We've got the critical numbers are places where your derivative is 0 or non-existent. And we're saying that at these critical numbers, you've got potential maximum or minimum values. And we just took the time to say, okay, maxes or mins just mean look at an open interval and it's a max, a relative max, if there's no value bigger than that on that interval. And on the flip side, the minimum is a relative minimum if on that open interval, there is no function value that dips lower than that spot, okay? And the critical numbers point us to those positions. All right, so why do those critical numbers point us to those positions? I've already kind of mentioned it in terms of when it's 0, because we can think of a horizontal tangent. So I think I'm just gonna go to the book here, because the book has nice pictures, and we like pictures. So starting with this very first figure, let's say that's some function. It's got this little curve going on. I don't know what the rest of the function does, doesn't really matter. But we can see that at this number C, there is a tangent line here that is horizontal. Back to algebra 1, horizontal lines have slopes of 0. So the existence of this derivative whose value is 0 points us towards this flat spot on our curve, this turning point on our curve, and thus tells us, oh yeah, that's a maximum value there, a relative max, because it turns around. The does not exist is a little bit trickier, but remember when we were talking about when derivatives might not exist, even though the function exists? And we talked about like gnarly cutbacks. If you got a gnarly cutback, like a cusp, that's often going to be a maximum or a minimum value, but there's no derivative there. So if we hunt out those spots where the derivative fails to exist, you very well might be looking at a relative extremum. Okay? The thing that is tricky though, and I mentioned this, is that word potential. 0 derivative, or the derivative equal to 0, or a non-existent derivative are necessary in order to have a maximum or minimum, but they are not sufficient. Just knowing that does not guarantee that that location gives you a maximum or minimum. And the great illustration, which we're not going to do because I think the illustrative power is literally in the illustration, not in doing it out. But in something like figure 6, which shows you the curve of f of x is equal to x minus 1 cubed plus 2, there is this flat spot in this cubic function where the derivative is 0. You have a horizontal tangent line. And yet, hopefully just visually looking at this, you can see this is not a maximum or a minimum value. It just is like a pause. But there's no way we can encapsulate C. I think it actually ends up being 1. At 1 is where we have this. There's no open interval you can contain 1 in where f of 1, which is 2, is either bigger or smaller than all values. Because if we try to do that to the left, open interval, remember, everything's going to be smaller. let's maybe do like to the right and left from 0 to 2. It's like, it's kind of just in the middle. It's just not a maximum or a minimum. So that does not guarantee a maximum or a minimum value. So we got to be careful there. Difference between sufficient and necessary. Okay. So I think we're ready to jump in and do some of these, because I think the more we talk, the less it makes sense. And we're just going to jump in feet first and start swimming. Yeah. It's been a lot of talking for half a page of notes, but I think we're ready. So we're going to start off with ejemplo numero. Example 1 seems like a good enough place to start. Okay, actually, I think I want to specifically write down what I just said, because that might be important. Okay. So what I mean by sufficient and necessary. It's like those are formal logic terms. If you ever take the LSAT, you will know sufficient and necessary like the back of your hand, or you will not do very well in the LSAT. What's the LSAT? It's the admission test to law school. It's a test of logic. Okay. Why do I know that? Because I took it at one point because I was going to be a lawyer, but it's dead. I became a teacher. Great choice. I mean that. I think the law would have been ill-suited for my personality. Anyway, if C is a relative max, oh, that was a bad way to put that. If C is a relative extremum, then f prime of C is 0, or f prime of C does not exist. However, does not work the other way. Not the other way around. So f prime of C equal to 0, or f prime of C dne, not sufficient to guarantee extrema. Okay, that's the conditional. The converse is not necessarily true. All right, now we're ready for example 1, hopefully. Example 1, critical numbers and extrema. If f of x is equal to x to the 4th plus 4x cubed minus 2x squared minus 12x. Okay. We're going to do two things in example 1. We're going to let our graphing utilities give us kind of an idea of where our extrema might be, and then we're going to use the notion of critical numbers that we established up here to confirm that those are in fact critical numbers. Okay. For now, we're not, or are we? Yeah, no, we're cool. Pretty cool. Okay. Graphing utility. Clear. Y equals. Clear. Clear. Get those paddles out. X to the 4th plus 4x to the 3rd minus 2x squared minus 12x. And then we'll go graph. Let's maybe extend our y down a little bit. Window. I'm going to cheat and see. Am I going to cheat? Maybe I'm going to cheat. I don't know if I'm going to cheat. Yeah, let's go down to like -20. Screw this up. Are we working the right function? X to the 4th plus 4x cubed minus 2x squared. Oh, classic mix-up. Forgot the 12. Sorry about that. 12x, not 1x. That'll make all the difference. So what we're going to do back to our regular window, I think that'll work. Go -10. Okay. Oh boy, so much better. Okay. So we can use this to kind of estimate where these extrema are. Okay. And again, remember back to pre-calc algebra 2. If we wanted to graph this, we could do a pretty good job. Okay. We could find some zeros. We knew the general shape because of the leading term needed to be a touchdown. We even could know like the amount of turning points, y-intercept, whatever. We could do a decent job. But now we're going to be able to zero in on where exactly those turning points are. Maybe not well where, but what they are too. And that's kind of cool. So kind of just tracing this thing is going to give us an idea. Let's start over here. So like visually, this looks like a max, this looks like a max, and this looks like a max. That was wrong. This looks like a min, that looks like a max, this looks like a min. Okay. So tracing. It's like maybe at 1-ish, at like -1, and like at -3 maybe. Yeah. So our guesses here are 1, -1, and 3 for our critical numbers, because those appear to be our relative extrema from our graph. So A, from graph, extrema appear to be at x equals 1, -1, and -3. But now we can confirm this analytically by finding the critical numbers. So if f of x is x to the 4th plus 4x cubed minus 2x squared minus 12x, then the derivative of f prime of x, is just a straight up polynomial, power rule all the way, 4x cubed plus 12x squared minus 4x minus 12. And so what we need is either, in order for this to be a critical number, in order to find a critical number, we need either f prime to be 0 or f prime to dne. Well, let's consider the second thing there. Is it possible for f prime to dne? Nope, because polynomials are differentiable everywhere. Polynomial function, the derivative exists everywhere. So we are specifically looking for f prime of x equal to 0. And I'll note that f prime exists everywhere because it is a polynomial. So the game here is we're going to set the derivative equal to 0 and see if we can solve for x. 4x cubed plus 12x squared minus 4x minus 12 is equal to 0, which would normally be kind of gross because it's a cubic, but I think Louis Leithold set us up with a bit of a softball, and I think this is going to factor by grouping. So let's pull out a 4x squared, leaving us with an x plus 3. And then we'll pull out a negative 4, leaving us with an x plus 3. Oh, happy day. This is really 4x squared minus 4 times x plus 3. I guess we could have factored out a 4 of everything, but that would have been smart, and I'm not very smart, so oh well. But now this will factor into 4 times, if we now factor out the 4, this becomes x squared minus 1, which factors into x minus 1 times x plus 1 times x plus 3. And using our zero product property from, I think, Algebra 1, we have indeed confirmed that if x is equal to 1, -1, or -3, f prime of x is equal to 0. Pen is dying. Here we go. New pen. Change it out. Therefore, 1, -1, and -3 are all critical numbers. And the thing that I hesitated earlier to say, which I guess we are not doing in this section, that'll wait until 3.4. But you might think, okay, well, if we identify the critical numbers, how do we then know if it is or isn't a relative extremum? And that will be something called the first derivative test that we'll do in section 3.4. And basically what we'll do is at these critical numbers, we'll just check on either side what the derivative is. And if it changes from a positive to a negative or vice versa, we'll say, oh, that's an extremum. If it doesn't change, then it's not an extremum. Because picture a curve. If you've got like positive derivative, positive derivative, positive derivative, positive critical number, and then it goes negative derivative, clearly that's a turning point. If it goes positive, 0, but then positive, that's that weird case where it's not an extremum. Okay, and so that's gonna be the first derivative test. For today, we're just interested in finding the critical numbers. Then we will later on in our life together make that call, is this or isn't this an extremum? Okay, so that's kind of big picture. Okay, do we need to do some more of these? Yeah, we probably should, you know, math, learning. Okay, we'll do a couple more examples and then we'll talk about the absolute maximum or minimum value, and then we'll probably be done, okay? I don't want to overcomplicate this, and maybe I already have, but I'm trying not to. We're just using the derivative to find critical numbers. Basically all we're doing. What are critical numbers? Derivative of 0, derivative of d and e. We can do that. We can all do that. I promise we can all do that. Nothing too scary here. Ejemplo numero dos. What do they want us to do? Find the critical numbers of the function defined by f of x equals x to the 4/3 plus 4 times x to the 1/3. That's a doozy. F of x is equal to x to the 4/3 plus 4 times x to the 1/3. Critical numbers. Well, critical numbers mean evaluating where the derivative is 0 or non-existent. It means we should probably find the derivative, which thankfully, thanks to 2.9, I believe it was, we now have the ability to use the power rule on rational exponents. And so we can find this. F primo of x, bring down that 4/3, take away 1 from that exponent. 4/3 minus 1 is 1/3 most days of the week. Same thing over here. We'll take down that 1/3, which becomes 4/3 when you multiply it by 4. Subtract 1 from 1/3, and you should get, I think, like -2/3. So that's fun. Which means, how do we want to do this? How do we want to do this? Is that how we want to do that? Yeah, I guess we should do it that way. Yeah, so I want to write this as a single fraction because we've now created a denominator over here. Is that how we're going to do this? Yeah. So we're going to do something a little bit non-intuitive, but you're going to see why in a second. I'm going to factor out this x to the negative 2/3. Okay. Actually, I'm going to do 4/3 since there's both 4/3. So 4/3, and this is kind of an important skill that we need to cultivate, is the ability to manipulate rational exponents. And I know we're all probably a little bit uncomfortable with that. So this is a good opportunity. So watch what happens if I pull out an x to the negative 2/3. Well, the easy part is the second part. I literally just factored this whole thing out. So we know that the second part's going to be 1. What about factoring out x to the negative 2/3 of this? Well, one way we can do this is just go in reverse. What needs to be here in order to give us 1/3 when we multiply by x to the negative 2/3? Because when we multiply like bases, we add their exponents. So to get to an exponent of 1/3, we need an exponent of 1, x to the first. So you can always check that you factored right. If you multiply this back out, x to the negative 2/3 times x to the first is in fact x to the 1/3. Why do we do that? Well, because now we can write this as a single quotient. Namely, we can write this as 4 times x plus 1 over 3 times x to the 2/3, which will make our life in finding when this is 0 or non-existent much easier than if we had done it when it was still a sum of two different things. This simplifies our life. Okay, so let's consider, when is f prime of x equal to 0? Well, it's going to be when the numerator is 0. Okay, and when the numerator is 0 is when x is 1. And when x equals negative 1, is there any spot where f prime of x does not exist? Certainly, when this denominator has a 0 in it, which is going to be when x is 0, because 0 to the 2/3 is 0. So f prime of x, I guess not equals, but d naught dne when x equals 0. And now here's a critical question that you need to pause and not get too excited. Are both -1 and 0 in the domain of f? Because that is one of the conditions of being a potential max or min. You have to actually exist on our function. -1 would be dicey if these weren't odd roots, but because these are odd roots, we're okay. Okay. And also since we're doing the 4th power on that one, so it turns it positive. But for 1/3, it's okay to have -1. 0 is also in our domain because 0 to the 4/3 and 0 to the 1/3, that's okay. So both of these are in our domain. If one of them had not been, that one would have been canceled out as a potential critical number. Both in domain of f, and therefore -1 and 0 are critical numbers. Cool. Cool. Try it out. Okay, we're cruising. I know this is kind of weird, kind of new, but we're doing good. Okay, final one of critical numbers before we jump into absolute extremum. It's gonna be fun, maybe. Ejemplo numero tres. Example 3. Oh yeah, trig stuff. If g of x is equal to sine of x cosine of x, why would we do this to ourselves? I don't know, because we can. Let's do some stuff. Derivative, we're looking for critical numbers. So g prime is going to be product rule. So the first thing, sine of x times the derivative of the second thing, cosine, the derivative of cosine is the opposite of the sine, okay? Plus the second thing, cosine, times the derivative of the first thing, the sine, the derivative of the sine is the cosine. So that's kind of a cute little function. G prime of x is equal to negative sine squared x plus cosine squared x. Okay, first we have to ask ourselves, is there any place where these things are not going to exist? No. Sine and cosine are forever cool. And when we add them together, it still works, okay? So what we're after for our critical numbers is when is this guy equal to 0? Well, if negative, or let's just say if g prime of x is equal to 0, then picture that. If this is 0 over here, then these two things have to equal each other. Because you can add sine to both sides. So sine squared of x is equal to the cosine squared of x. So when are those two things equal? Well, we can simplify that. If the squared values of sine and cosine are equal to each other, it must be because the non-squared values are equal to each other. So now we have to think, we have to picture the unit circle. When do sine and cosine have the same value? Well, it's not just at one place, because remember, trig functions are cyclical. They go on forever. So it's when we have 45-degree angles all the way around the circle. Forever and ever and ever and ever. If you do that long enough, you will get dizzy. Okay? So when x is equal to pi over 4, when x is equal to 3 pi over 4, when x is equal to 5 pi over 4, when x is equal to 7 pi over 4, when x is equal to 9 pi. Do we have to sit here and list all these? No, that would take forever because it's literally an endless list. So let's be smart. It's pi over 4 plus all of those half pi, those 90-degree additions. From 45 to 135, from 135 to 215, sure, to whatever, okay? We're just adding 90 degrees. Don't make me think. So that means plus pi over 2 times just whatever number we want, times k, for k an integer. So those are all of our critical numbers. We have an infinite number of critical numbers. Okay, so that's fine. That's cool. Good. Okay, deep breath. If you want, you can press pause, maybe go take a walk, because now we're going to not change gears, just maybe change gears. Very slightly. We're still riding a bike, it's just slightly different angle. Okay, and I think what do I think? Probably thinking too much. That's okay. Absolute minimum value and maximum value. Yeah. So definitions, and then some examples, and then we'll put a bow on this. Okay. So remember, we took that time to do the relative max and min, and I stressed that it was on an open interval. We are now going to look at absolute maximum and minimum, absolute extremas, which requires a closed interval, okay? A closed interval. And that's our Pavlovian response when we see a closed interval in the AP test and they're asking about like maximum production of some function. They're asking about the this theorem. And we're gonna have to make sure that we show the extreme value theorem. Okay, so maybe we're gonna start there. No, we're going to define absolute maximum and minimum values. But we're going to cheat again, and we're going to do it as one definition because ain't got no time for two definitions that are essentially identical. Okay, so 3.1.5 and 3.1.6 definition of absolute max or min on an interval. So the function f has an absolute, not relative anymore, but absolute maximum or minimum value at C. No, absolute maximum or minimum value on an interval Does this really not include a closed interval? We're going to say closed because I think it's supposed to be closed, even though the definition doesn't. Add into the definition. On a closed interval, if there exists absolute maximum or minimum some number C in the interval such that f prime of C is greater than or equal to f of x max, or f of C is less than or equal to f of x min. For all x in that interval. Okay, so closed interval, that's the only difference here. Cool, which leads us directly to something called the extreme value theorem. We got critical stuff going on, we got extreme. It's a dramatic lesson. Mr. Smith talks about calculus. Extreme. Okay, 3.1.7. L extremo value theorem. No sé cómo decir value. No sé, no conozco. No sé. You saber things, you conocer people. There's a distinction there. That sometimes we saber things, but we don't really conocer. The depth of feeling that happens with conocer. So, oh, you think you saber calculus, but do you conocer calculus? I don't know. Someday. That's our aim, for everybody to conocer. Saber is fleeting. Saber is superficial. Saber is a 3 on the AP test. Conocer is a 5 on the AP test. Conocer calculus. Why are we whispering? I don't know. The extreme value theorem says if the function f is continuous on the closed interval. Closed interval is like, again, Pavlovian response. Closed interval, you should be thinking extreme value theorem from A to B. Then f has an absolute maximum value and an absolute minimum value on A to B. Seems like a pretty bold thing to say. So you're saying that they have to be there? Yes. Okay. If it is a closed interval and you have a continuous function, somewhere on that interval, there is an absolute maximum where no other value on that interval is more than it, and there is an absolute minimum where no other value on that interval is less than that value. Okay. And so visually, you can kind of picture this. So options. The easy ones are where nothing interesting happens, okay? Or not interesting enough to merit the endpoints not being your max and min, okay? So this is gonna be kind of tight. I don't think it's in the book, but I think this is helpful before we jump into some problems. You could have an interval from A to B. Where your curve is just kind of like, maybe it does some stuff, but it's just doing stuff to do stuff. And in this case, there's your min. And then f of b is your max. Okay, the endpoints are your extrema. And this would work in the opposite direction. I don't think I'm going to draw it. But if you had like a decreasing function, then f of a would be your max and f of b would be your min. And nothing in between does anything of interest enough to become an extrema. Okay? So then at that point, endpoints are extrema. What we're going to kind of be checking for is there anything in between here for like another option? Sorry, probably should use a straight edge here. Oh well. Oh, that vertical axis is wonky. Sorry about that. Let's say you had A and B, some closed interval, continuous function, and you've got a curve that goes like that, let's say. Now, if we look at these endpoints, there's f of a. There's f of b. Clearly, on this interval between a and b, there are values that achieve both larger and smaller values than either f of a or f of b. And those will be our absolute extrema. Okay, so this would be like c, f of c, or maybe c1 would be our max. And c2, this low point, would be our min. So the extreme value theorem just says they exist. They might just be the endpoints, but they also might be somewhere in between those endpoints on your closed interval. And so our process for applying this extreme value theorem is to find the critical numbers, see what the function's value is at those critical numbers, and then compare them to the endpoints and see if they qualify at either your biggest or your smallest. Because those are your only options. They're at the endpoints or they're somewhere in between at a critical point. Okay? And so that is going to be exactly our process, which I will list on the next page, is finding the critical numbers, finding the values of your endpoints, and then comparing. And whatever is the biggest is your maximum, whatever is the smallest is your minimum. Okay? It's not rocket surgery, but you just got to follow the steps. Okay? And the closed interval thing is what sets us into motion. That because we have a closed interval, we know that these values are on that interval and that those are potential extrema. Okay? So here are the steps we'll take. So finding absolute extremum. Or in other words, applying extreme value theorem. Three-step process. Find the function values of the critical numbers on the interval from A to B. Technically, it's the open interval when we're doing the critical numbers because it can't be the endpoints, but you don't need to stress out about that. 2 is find the values f of A and f of B, and then just compare them. Pick out the biggest and the smallest. Largest value from 1 and 2 is absolute max. The smallest value is the absolute min. Okay, so that was a lot of talk. Now let's do some math. Example 4. We're going to apply the extreme value theorem. If f of x is equal to x cubed minus 6x minus 1, find absolute extremum on the interval between -2 and 3. Okay. So first thing we need to do is find the critical numbers. So 1, find critical numbers. Which means finding the derivative of f, which is f prime of x. So f prime of x is 3x squared minus 6. And so if we want this equal to 0, because there's not any non-existent places on a polynomial, we want this equal to 0. Means that this is equal to 0, so 3 times x squared minus 2. Which means we want x squared minus 2 equal to 0. We want x squared equal to 2. In other words, we want x to equal plus or minus the square root of 2. Okay. Now, and actually, as I'm writing these, this is fine to do these steps. I kind of, and especially on the AP test, it's sometimes nice to clearly display your work, or just succinctly. So the function values at f of -2 and f of -3, positive 3. But here's what we're going to actually do. I'm going to make a table. X, f of x. Our endpoints are -2 and 3. And we just found that our critical numbers are at -√2 and +√2. And now we're just going to fill these in and figure out what's the biggest. Okay? Because you've done the work to show where these numbers came from. So now we can go to the table and just analyze. So let's go back. So this is now back to f of x. So let's delete this. Let's say f of x is x raised to the third minus 6x minus 1. Second quits. And we want vars y1 of -2, which gives us -5. So far, that's the winner for, well, minimum and maximum. Let's go y sub 2 of 3. So let's check the endpoints first. So second, enter. Let's do, oh, I done botched. It's supposed to be a -2. That's where somebody should yell at me. But you guys aren't here to yell at your teacher, which I guess is maybe a good thing. But sorry, it should be 3. Whew, crisis averted. Okay, now second enter. Let's do 3 is 8. Okay, so as of right now, this is our absolute min, this is our absolute max, unless either one of these values is either less than or greater than one of these, either 3 or 8. So these are the endpoint values, leading contenders. We need to now check if either of these values outdoes either of those two. So second enter. Negative second square root of 2. So we'll call that 4.65. Doesn't really matter since it's not going to do anything for us since it's neither smaller than 3 nor bigger than 8. So not an absolute max or min. And then second enter again. We'll do the positive version. Ooh, look at that. Winner, winner, chicken dinner. Negative 6.7, let's say. Now that we've got this all laid out real nice and neat in our table, it's real easy to see, oh, okay, this is our absolute max. I said that wrong, absolute min. And this is our absolute max. Okay. And then this is what has been tripping up math students since we introduced the idea in like Algebra 2. So the absolute maximum value on this interval and people mess this up, they do all this work and then they say the wrong thing. Absolute maximum is 8. That's the absolute maximum value. It occurs at 3. At x equals 3. And the absolute min is negative 6.7 whatever. Okay. It occurs at x equals square root 2. Okay. So don't get all this way and say the absolute max is 3 and the absolute min is square root 2, because it's not. These are the values. Those are the function values. Okay? Which is why the table is nice too, because it helps us avoid that error, I think. Because it says clearly, oh, yeah, the value is 8. The value is negative 6.5. They happen at these locations, but the absolute maximum or minimum are function values, not x values. They are y values. That helps your brain. Function values. Okay. Do we need to do another one? Do we have time? Yeah, we've always got time. We're doing this again. We're doing this again. Yeah, we're okay. We're okay. Example 5, and then we're done. Is that really it? Example 5, and then we're done. Oh yeah, because then they try to prove it, and it's gross. We don't need to prove it. Okay. Example 5, and then we'll call it a day. This has been a long lecture, but it's all just one, and then we're done. Example 5. If your function is f of x equals x minus 2 to the 2/3, and our closed interval is on 1, 5. Let's just do this thing. Crank her out. Step 1, critical numbers. F prime of x, good thing we know the power rule for rational exponents. Says we can pull this down 2/3 times x minus 2 to the negative 1/3. Technically, there would be a chain rule here, but the derivative of x minus 2 is just 1, so it's not much of a chain rule. And so then this becomes, let's say, dose over 3 times x minus 2 to the 1/3. Okay. Is there anywhere that this is going to equal 0? No. You got 2 there. There's never going to be a 0 value here. However, you might have some DNEs. And the DNE in particular is going to be when this denominator is 0, which is exactly when x is 2. Okay. So f prime of x DNE when x equals 2. Okay. Second step, we're going to make our table. So there's only one critical number here, so that's nice. Our endpoints were 1 and 5, and our critical number we just identified is 2. Do we even need that? Do we? Maybe? Sure. So y equals, or no, we'll just do this. Work out students. So f of 1 is going to be equal to 1 minus 2 squared cube root. Okay, which is like the cube root of negative 1 squared. That just turns out to be 1. Cool. Okay, this is a little tricky, and this is where we can definitely get tied up. We said that f prime of 2 did not exist. However, that doesn't mean that f of 2 does not exist. So f of 2, 2 minus 2, oh, 0. Okay, so far that's the max, that's the min. When we plug in a 5 here, let's see what happens. The cube root of 5 minus 2 squared, that turns into a 3. You square that, you get a 9. You want the cube root of 9. Off the top of my head, I don't know what that is. Let's maybe go to our calculator for that one. But I'm guessing it's bigger than 1, but who knows? So 9 raised to the n3rd power, 2.08. Now we just pick out the biggest and the smallest. Smallest. Absolute min. Biggest. Absolute max. And then, of course, being careful as we write this. Oh, hello, come to the party. 3. Absolute max is the cube root of 9, which occurs at x equals 5. Then the absolute min is 0. And it occurs at x equals 2. Woo! Okay, so that was a lot. Ooh, stop that. Okay. But we should now be equipped to tackle the ejercicios de lesson 3.1. I'm going to press pause here because that might have been a 90-minute, not quite 90 minutes, but it's all done. Okay, we're all done with, no, I don't want to invite. I'm going to stop share, and I'm going to press stop recording.